Okay, looking at some U-substitution with exponential functions. In these problems, if you're a random internet passerby, if you want to look at these problems, it's from a sheet that I handed my students, and it can be found at bit.ly/int-temp, int-temp. So let's look at the first problem. So we have 2x e to the x squared. When you have exponential functions, and for those of you who have forgotten what the word exponential means in math, it means you have a number to a variable power. So when you have like 4 to the x or e to the x or anything like that, that's your exponential piece. And for exponential functions, when you try u sub, you first look in the exponent of the exponential. So I'm going to let u be x squared. And if u is x squared, then the derivative of x squared would be 2x. So I want to find my u prime, which is sitting right here. So I have my u, I have my u prime, and when you substitute that out, your u prime and the dx, so the 2x becomes your du, e to the x squared. Well, I didn't touch the e, I'm not substituting that out. I'm leaving the e, but the x squared will come out, and I will substitute u in its place. And so we're left with the antiderivative of e to the u, and e to the u's antiderivative is e to the u plus c, and then we'll plug the u back in. So we have an answer of e to the x squared plus c. Boink. All right, moving on. There's that one again if you want to see it for a few more seconds. All right, that's good enough. Okay, so 7 to the x. This one is going to be a bizarre u substitution because for my students, I believe this is the first time this will occur. There just doesn't seem to be a whole lot in this problem. So you might be thinking, why isn't this letting me pick? There we go. You might be thinking, well, there's an exponent. Why don't I let u be x? Well, if u is x, u prime would be 1. And if I did that, I need to see my u prime, and yeah, there's a hidden 1 there. You could say it's 1 times 7x, or 7 to the x. So there's my u prime. So I have a u and a u prime right here. The problem is, if you let u equal x and you go through the substitution, then you end up with 1 being my du, and the dx kind of comes out with that. And the 7 I didn't touch, but it was 7 to the x power, and x is equal to u, so I'll substitute u in its place. If you ever choose the substitution u equals x, it will accomplish nothing other than changing the variables from x to u. Because if you look at this, it is the exact same function we started with. The whole point of u substitution is to change the original problem into an easier problem, which is what happened on this one. It was really ugly. I had an x squared and a 2x. Those went away, and my u sub actually cleaned up my function. This case didn't happen. The moral of that, and the reason I went through the time showing you that, is you never, ever, ever do u substitution with u equals x. It never accomplishes anything. So make sure that when you do u sub, u is something other than just a single x. So I'm going to have to start over on this one. And I'm going to do something really bizarre just this one time. Just this one time. I'm going to go crazy and say, what happens if u is equal to 7 to the x? What if I just take the whole thing and make it u? Okay, so u is 7 to the x. What is the derivative of 7 to the x? Well, it's an exponential function. The derivative of that would be 7 to the x times the natural log of 7. And technically times 1, because you want to multiply by the derivative of the exponent, but that's not needed. So my original problem, which I'm going to rewrite and give myself a little bit of room here, it's 7 to the x dx. I've told you many times the most important part of u substitution is you must find the du. If you don't see du, you have to start over. So in this case, I'm looking for 7 to the x, natural log 7. I must find 7 to the x, ln 7 in the problem. I have 7 to the x, I'm missing ln 7. Well, ln 7 is just a number, and if you're missing numbers, you can stick it in there. So I'll stick an ln 7, but I have to offset with 1 over natural log 7. And in this case, when you identify the u prime, which is always the first thing you identify, you always identify the u prime first, that actually takes everything. The whole function is now gone, and the whole thing has turned into a u prime, which means when I do the substitution, all that's left is a du. all that's left is a du. There is nothing remaining to plug my u into, and that's okay. As long as you take care of du, that's all that matters. I do still have a 1 over natural log 7 on the outside. And this new antiderivative, the antiderivative of du, well, there's an understood 1 stuck between those two. That's a messed up looking 1. And the antiderivative of 1 would just be u, and there's still an 1 over natural log 7 in front. Right, so we have 1 over natural log 7 times u, but u is 7 to the x. So my answer is actually 1 over the natural log of 7 times 7 to the x plus c. So there's your answer. And that is one that I have given my students as a memorized formula because it's just a little bit quicker. The antiderivative of any number to the x will always end up being a to the x over the natural log of a. It's more efficient. Sometimes memorization is more efficient. And so I would recommend you memorize that one because it's quicker just to say, a to the x over ln a versus all this garbage. Okay, moving on. Okay, 31, we have e to the negative 3x. This one's going to be a little bit easier than the last one. I see in the exponent, what I told you earlier, you're going to start by letting u be the exponent. And so I'm going to say, well, what happens if u is negative 3x? U prime would be negative 3. So I have to see negative 3 in my problem. There's not one, but I can fix that by shoving a negative 3 in here. We will offset with a negative 1/3. And there is my u prime. You must identify the u prime before you proceed. Right? So I'm going to substitute my u prime in. We have negative 1/3 on the outside. Antiderivative, negative 3 is my du. But I'm still left with an e to the negative 3x. So I'm going to have e, and negative 3x comes out and becomes u. And now we're back to the nice antiderivative of e to the u, which is e to the u. But u is negative 3x. And so I will just leave the answer as negative 1/3 e to the negative 3x and move on. And this is the last one. Okay, so the antiderivative of 5x over e to the x squared. For this problem, what I think I'm going to do, and I just know to do this from experience, I'm going to rewrite the problem as 5x, and I'm going to bring that whole bottom up to the top, and instead of e to the x squared, I'm going to bring it up and make it e to the negative x squared. It will make this problem a little bit easier. So now when I do my substitution, my u, I'm going to start with the exponent. Let u equal negative x squared. If that's my u, my du needs to be negative 2x. But I have a 5. I think what I'm going to do before I go on, I'm going to take this 5 and pull it out. And so my problem becomes 5 antiderivative of x e to the negative x squared. Now for my du, or for my u prime, I'll change that to u prime, whatever. For my u prime, I need to put a negative 2. We'll offset with a negative 1/2. And now I can substitute. There's my u prime. There's my u. So there's u prime. And so we're left with, after the substitution, 5 times negative 1/2 is negative 5/2. Antiderivative, negative 2x. There's my du. E to the negative x squared will become e to the u. And again, the antiderivative of e to the u is e to the u. So my answer, the negative 5/2 on the outside will stay there. E to the u becomes e to the u, but u is negative x squared. Slap on a plus c, draw a box around it, and move on. So there we go. There's a few examples of integration with U-substitution as it pertains to exponential functions.